our ambassadorial lectures co-organized by Embassy of Japan in Indonesia, TOHOKU University, and Center for Japanese Studies, Universitas Indonesia. Today's lecture entitled Future Technology of Geothermal Energy for Sustainable Development. First of all, we invite Dr. Diah Madubranti, Head of Center for Japanese Studies, Universitas Indonesia, to give an opening remarks. Ibu Diah, yoroshiku onegai itashimasu. Ibu Diah, please unmute first. Tolong di unmute dulu, Bu.
Good afternoon, konnichiwa. Welcome to Tia Noriyoshi Sensei and all participants. Nice to meet you at second series of the 9th of Ambassador Lecture Series. Future technology of geothermal energy for sustainable development, which is conducted by Center for Japanese Studies, Universitas Indonesia, in collaboration with the Embassy of Japan in Indonesia. We are pleased to announce you that our honorary speaker today, TSUCHIYA Noriyoshi Sensei, is Dean Professor, Graduate School of Environmental Studies, TOHOKU University, Geomaterial and Energy Laboratory, Japan. He specializes in geochemistry, material engineering, and geology. The material presented by Professor TSUCHIYA will certainly be very interesting for participants because it is very contemporary. By this lecture, I hope we can gain more knowledge from him, even though we are still in the pandemic situation now. I hope this lecture will be useful. Last but not least, TSUCHIYA Sensei, we also hope that we can meet again in other events organized by Center for Japanese Studies in Universitas Indonesia. Thank you and enjoy the lecture.
Thank you very much, Ibu Diah Madubranti, for your opening remarks. And now I invite Mr. Takahashi Yusuke, Secretary of Education, Embassy of Japan in Indonesia, to give an opening remarks. Takahashi-sama, yoroshiku onegai itashimasu.
Thank you very much. Professor Noriyoshi TSUCHIYA, Ibu Diah from University of Indonesia, all the staff member of the University of Indonesia, Center for Japanese Studies, and all the audiences participating from all over Indonesia and maybe from all over the world. Representing the Embassy of Japan in Indonesia, it is my pleasure on holding this 9th Ambassadorial Lecture series. Starting from 2012, Embassy of Japan in Indonesia has co-hosted this Ambassadorial Lecture series with Center of Japanese Study in University of Indonesia. We have been holding this event so that lots of people will be interested in the culture and technology and all the customs of Japan. Today's theme, the future technology of geothermal energy for sustainable development, is quite relevant for both Japan and Indonesia. I am sure that today's lecture will be quite interesting. I hope today's opportunity will be a precious one for all the people who will have further interest in Japan. And I hope lots of students who are participating today will put Japan as one of your options to continue study and research. Thank you again for all the preparation for the staff member of the Center of Japanese Studies in University of Indonesia. And please enjoy today's lecture. Thank you very much.
Thank you very much, Mr. Takahashi Yusuke. And now we will go to our main session, our lecture, a lecture by Professor TSUCHIYA Noriyoshi. Today, I, Rolly Esther, will serve as a moderator for this session. Before TSUCHIYA Sensei deliver his lecture, let me introduce a little bit about him first. Professor TSUCHIYA Noriyoshi is a dean and professor at Graduate School of Environmental Studies, TOHOKU University. He studies water rock interaction involving geothermal and metamorphic fluids under various earth scientific situations. He also carries out hydrothermal experiments for understanding rock subcritical and supercritical geofluids interactions. Without further ado, please welcome TSUCHIYA Noriyoshi Sensei to deliver a lecture. TSUCHIYA Sensei, yoroshiku onegai itashimasu.
Okay, thank you very much for very nice introduction for me. And thank you very much, dear Madhuranti-san and Takahashi Yusuke-san and Lowry-san. Thank you very much. So I'd like to start my lecture. So I want to share a slide. Okay. Okay. Okay, can you see my slide? It's okay?
はい、大丈夫です。OK です。
Okay, so shall we start today's lecture? Now, Japan is 4 o'clock. We have 2 hours difference between Jakarta and Japan. And now it's the Friday evening, but today is very fine and not so cold. And it's very good weather in Sendai. So the title is my talk is Future Technology of Geothermal Energy for Sustainable Development. So this slide is the founder of Sendai City. He was born in about 400 years ago, and he is a founder and the king of Sendai City. So, and Sendai is located, yes. So Sendai is here, Tokyo is here, and Sendai is 400 kilometers north from Tokyo. And the Sendai's population is about 1 million. It's a relationship, the Tokyo and the Sendai is similar to Jakarta and Bandung. The Jakarta is a very huge capital city, and Bandung is the relatively small city and a very comfortable city. And Tokyo and Sendai is almost same relation. Tokyo is very huge, and I don't like Tokyo. It's very noisy city and dirty. So, and the Sendai is the green city. The nickname, our city name is Green and Forest City. We have many trees in and outside cities. And Sendai is an academic city, so we have many universities. And so it's similar to Bandung. And I've been to Indonesia many times, maybe more than 20 times. And because we have a satellite campus in the Bandung Institute of Technology. So I've been to Bandung many times. And I already realized the flag, national flag of Japan and Indonesia is almost similar. So the color arrangement is the same, the red and white, but the shape is different. In Japan, we are circle, which means this is a sunlight. The meaning of Japanese national flag is the sunlight. And this is the Indonesian national flag. I just now, my student told me the meaning of this flag. So the red is brave, and white is holy. Is it okay? Okay. So, responsibility is my student, not me. Anyway, so Japan and Indonesia, we have very close relations. And the Tokyo University, we have many Indonesian students, more than 100 students. They are studying in Tokyo University. So today's talk, the introduction and the geothermal energy in the world, and the geothermal energy in Indonesia and Japan, and the geothermal energy system and the future technologies. This is the structure of today's talk. Anyway, I'm a geologist, I have been to Antarctica 3 times. And so some of my students studied the geology of Antarctica. The Antarctica is very cold continent and covered by the ice. The 98% of Antarctica is covered by ice, but the 2% we have several outcrops. So we collected rock sample from this outcrop, and we analyzed the characteristics of rocks, and we considered about the tectonic history of Antarctica. And also, I've been to many countries, and the Mongolia, the Russia, and the El Salvador, and also I have been to Indonesia many times for studying about the geothermal energy. Anyway, I'd like to go abroad, but unfortunately, due to COVID-19, last year I couldn't visit any overseas countries last year, 2020. So I really hope to go to Indonesia to 2021 this year. So everything depending on the COVID-19. So before the talk, I would like to talk about the Great East Japan earthquake and tsunami disaster. Just 10 years ago, 2011, March 11, 1446 Japan time, we had a very big earthquake, magnitude 9.0 in the Richter scale, and at that time we had a very big tsunami disaster. So after that, the energy system, energy concept, energy society, it just changed after this earthquake and the tsunami disaster. So we took the photograph of the tsunami area by myself. So you can see the car on the top of the mountain, top of the buildings. It's the 3rd floor of the mountains. So the depth, height of the tsunami is more than 30 meters. And here is the bus on the top of the roof. So the strength of the tsunami is quite huge. And after that, we have to think about the disaster science and also the new energy system for sustainable development. So this is another photo, the fishing boat on the road. So the boat is on the road. And also, after the great earthquake and the tsunami disaster, we have the big issues. So this is the Japan Island. And the Tohoku University Center is here, and the Tokyo is here, and here is the Fukushima Daiichi nuclear power stations. So the Fukushima Daiichi nuclear power station was damaged by tsunami attack. So this is the 4 nuclear reactors, reactor 1, and reactor 2, reactor 3, and reactor 4. And all of reactors are destroyed by the tsunami and the hydrogen explosion. So still now, 10 years already passed, but still now about 50,000 people cannot go back to their own home. So they have to leave another cities, another place for prohibiting. Just now we have an earthquake. This is aftershock of great earthquake. So about 10 years ago, we have a very big earthquake. And so still now we have some earthquake about the aftershock of great earthquake. So just after 1 year before, we had a very big aftershock. Anyway, so the great earthquake and the tsunami disaster, the Fukushima nuclear power station was damaged. And this accident is still affected by the energy policies and energy communication in Japan. So the geothermal is the most promising renewable energy in Japan and also in the world. So this is the Chinese character. This is the meaning of this character is geothermal. The pronunciation in Japanese is chinetsu. This is the geo or earth or ground. And this is the meaning of this kanji character is heat. So this is the geo heat. So the geothermal. This is the meaning of this kanji character. This is a Chinese character. Okay. So this is the geothermal energy or potential in the world. So this is the number of active volcano. This is the number of active volcano, and this is a geothermal potential. And the geothermal potential, number one country is United States. So United States of America is a very big countries, and particularly the West Coast, the Washington State and the Oregon and the California State, the Utah, the Nevada, the west side of United States, they have several active volcanoes and the fossil volcanoes. And the number of the active volcano is about 160 in United States. And the geothermal potential is 30 megawatt. So number one in the United States. And the number two country is Indonesia, as you know. So number of the active volcano in Indonesia is 146, and the potential geothermal energy is almost 28 gigawatt. And the third country of Japanese the geothermal energy is Japan. So we have 119 active volcano, and the geothermal potential is about 24 gigawatt. So Indonesia is number two country, and Japan is number third country in terms of geothermal potential. So we have the huge potential of geothermal energy. And this is a geothermal development. And so here is 1950, 1960, 1970, and here is 21st century. And this is installed capacity, and 10 gigawatt and 20 gigawatt here. And from 1950, so Italy is the first country to generate the electricity by geothermal. And 1950 is the birthday of geothermal energy. And increasing. And here we have the two oil crises. One is 1974, another the second one is 1979. We have the second two times oil crisis. After the oil crisis, the many countries wanted to develop geothermal energy. So the installed capacity is increasing rapidly. And here it's 2011, we had the nuclear accident in Fukushima. After that, and also we face to the green and carbon neutral policy and concept. So the development of geothermal increasing very, very rapidly. So Japan is here. It's very low. And Indonesia is here. So now Indonesia is 4 gigawatt. The installed capacity is 4 gigawatt in Indonesia, and Japan is only 600 megawatt. So later I will explain why Japan is very low. So, but actually we have the great potential of geothermal energy. And the Indonesia, the potential is 28 gigawatt, and the installed capacity at the moment is only 4 gigawatts. So the 4 gigawatt divided by 28 is almost 14%. So only the 14% of potential are already developed. But you have the great potential of geothermal energy. And the geothermal share for electricity in Indonesia about 2%. And in contrast, Japan, we have the installed capacity is 600. And this is the potential of geothermal energy. The 600 divided by 24 gigawatt, it's only 2.5% of geothermal energy was developed in Japan. And the geothermal electricity share is very low, extremely low, less than 1%. The electricity by geothermal in Japan is only 0.2%. So we have a great potential, but the development of geothermal is not so well developed in Japan. So this is and the facility of the utilization rate, geothermal is 83%. Geothermal, the power plant can generate electricity for 24 hours in a day. So almost it's possible to generate electricity for 24 hours in a day. So 80% of facility utilization rate is it's a sample maintenance time. So 1 month in a year, and sometimes 1 month in 2 years, we have to do the maintenance. So at that time, we have to stop the power plant. So the facility utilization rate is not 100%. So 83%, sometimes 85%. So but actually the geothermal facility utilization rate is very high, over 80%. And instead of geothermal energy, the wind and solar efficiency is quite low. So the wind, in case of wind power, is about 20%. And so if there is, it is very comfortable day. So in that case, we have no wind. So in that case, it is impossible to generate electricity by wind. And the solar efficiency is only at 12%, very low. So the daytime, so it's impossible to generate electricity, of course. And in the cloudy day, the rainy day, the snow day. So Indonesia, there is no snow, but in Japan, we have a snow time in winter season. So in that time, it is impossible to generate power electricity. So the facility utilization rate of the solar is only 12%. So the solar energy, installed capacity of solar energy is in the world, about 20 gigawatt. But so please think about the facility utilization rate. The geothermal is over 80%, but the solar is only 12%. So the geothermal and the utilization rate is 7 times higher than the solar. So the 20 times 7 is 100, is in the world 300, but actually the geothermal capacity in the world is about 140 gigawatt. So you can see the power solar panel many places. On the roof, on the park, sometimes in the forest, you can see is a point. It is not so familiar with the ordinary people, but actually the installed capacity is almost half of the solar energy in the world. So geothermal has a great potential as a promising renewable energy. And so Japan is the geothermal development is not so good at the moment. Geothermal power turbine to the world. So here it's the Mitsubishi Hitachi Electric Company. The share of the turbine, geothermal plant turbine, is about 24%, and the Toshiba is 24%. And the Fuji Electrics is 20%. So actually, the 3 top the Japanese the turbine occupies the market of geothermal power plant in the world, 70%, 68%. So 68% of geothermal power plant turbine in the world is made in Japan. But actually, the geothermal development, the United States is 28%, and Finland, Italy, and New Zealand, and Africa, El Salvador, and Kenya, and others. So Japan, Indonesia is the third country as a geothermal development in the world. And Japan is the top country to export geothermal power plant turbines. So 68% of turbine market is 21 years already passed after the 21st century. But actually in the world and also in Japan, the fossil energy is the main energy resources in Japan, in the world, also in Indonesia. So Japan is now almost 90% of the primary energy is after the 2011, almost nuclear power plant in Japan was stopped. Now it's 4 and 5 nuclear reactors are operating now in Japan. So the share of the nuclear energy is increasing to increase in Japan. So instead of nuclear energy in Japan, the fossil energy is the dominant energy resources in Japan. And also the world was the same, almost 96% of the primary energy supplied by the oceans and Chile, and the Central America and the United States, the West Coast, and Japan, the Philippines, and also the Indonesia and New Zealand. The outlook in 2018, so Indonesia is almost same. So 39%, the coal is 33%, the gas is 19%, the hydro is 3%, geothermal is only 2%, and the solar and biofuel are here. So Indonesia is the same world in Indonesia and also in Japan. And Indonesia has the very great plan of geothermal development in Indonesia. Now, the 75 working area, the total capacity of the plant is about 8 gigawatts. So you have many development plans in Indonesia. So the distribution of Indonesian geothermal prospect, the potential, the Sumatra is about 14 gigawatt, and Java is 9 gigawatts. So almost 2 big islands, Sumatra and Java, both of them are the great candidate for development of geothermal energy in Indonesia. Unfortunately, I never been to Sumatra, and sometimes I told with my student from Indonesia, I'm very, very afraid of Sumatra thing. So it is impossible to visit Sumatra. So Java is safety for me. Okay. Anyway, so the Sumatra and Java, both of them are the great potential of geothermal energies. And this is a spatial distribution geothermal project. It's the Java existing and the Java new one, and the Sumatra and the East new. So the Sumatra and the Java is the great candidate of geothermal energy in Indonesia. And in Japan, we have two regions in terms of development of geothermal energy. So one is TOHOKU. TOHOKU means northeast. TOHOKU means northeast. And another one is Kyushu. So in Japan, the TOHOKU University and the Kyushu University, both of two universities, the representative university which studies of the geothermal energy. So if you want to study geothermal energy in Japan, so you can select two universities, TOHOKU University and Kyushu University. And the two universities have different characteristics. The Kyushu University they are studying about the conventional geothermal energy. So it's very close to industry. So they study about the conventional geothermal energy. It's a very practical and maybe good exercise. And the TOHOKU University, we are the research university, and also we are conducting the new project and the future technology of geothermal energies. So not only conventional, but also we really focus on the future technology of geothermal energies. So Kyushu University and TOHOKU University, we have different characteristics. So you can choose. You can choose the two universities, yes, of course. But really, actually, I recommend TOHOKU University is better. Anyway, Kyushu is also a good university. So the geothermal potential in Japan, so this is Hokkaido, is a northern island, and here it's the Tohoku, the brown color is the Tohoku, so Tohoku district, and here is the Kyushu, that's the Tohoku. So 33% of geothermal potential is in Tohoku district, close to our university. And the geothermal field in Japan, so this is Lardero, the Wairake, the geysers, Afuachapan, and the Hachobari in Japan. The Lardero, Italy, the Wairake, New Zealand, geysers, United States, Afuachapan, the El Salvador, and the Thai, Philippines, and Hachobari in Japan. And area, the Lardero and the geysers, is a very huge area. And so, but Japan is the very districted area. So Japan, the area is very small, but this is the thermal density. So megawatt electricity per square kilometer. And the Lardero is only 2.2, and the geysers is 13. So it's huge country has a very low density of geothermal. So Japan is a small country. So as you know, Japan is an island country. So the Indonesia also the island country, but your country is a very big island, Sumatra and Java, very big, but Japan is a very small country. But so but area is very small, but the thermal density is very high. That is the characteristics of geothermal energy in Japan. Not big area, but high thermal density in Japan. So United States, is a very huge country, and so they have very huge potential of geothermal energy, especially in the west side, the California and the Nevada and the Utah and the Oregon, the Washington State. So actually Nevada, they have the big resources of geothermal energies, but actually Nevada is a desert state. It's not so much population. So, but California state, they like renewable energy, and the solar, and the geothermal, and also the wind. So the system of geothermal energy is very, very simple. This is a cap rock, and this is a geothermal reservoir, and this is a cool discharge water comes into this geothermal reservoir and heated up. And we can take hot water from the geothermal energy, geothermal reservoirs, and the power plant and the cooling tower that inject the geothermal fluid to the geothermal reservoirs. So this is a circulation system, and this is a heat, and so the geothermal is a renewable and sustainable energy system. So this system is almost same as the thermal and the nuclear, the geothermal. It's almost the same system, but some parts is different. So because the geothermal fluid is not pure and clean fluid, so the power plant has a special equipment are required in geothermal power plant. But the total system is not so complicated in terms of conventional geothermal system. And also the flash steam power plant is the production well and the separation from the fluid and the steam. So we don't need fluid. We need only steam. The steam and here and the turbine and the generator and the electricity, and the steam is cooled down by the river water and sometimes sea water, and using the cooling water, and they inject into the geothermal reservoir again. So this is the circulation system. This is the process of geothermal energy. So in Japan, the first geothermal power plant is developed in 1966. And in 2016, we had a 60 years anniversary. So we have a 60 years history of geothermal development in Japan. So the geothermal is the most promising renewable energy in Japan, of course, but we have only 600 megawatts, and it's very low ratio of the geothermal energies. Why in Japan we cannot develop the geothermal energy? So we have some problems. So the geothermal issues in Japan is national park problems. So 80% of geothermal resources is inside the national park. So the national park are strictly prohibited to develop the geothermal energies. But we have several technologies to develop the geothermal energy inside the problem. And another one is the hot spring problems, the disagreement of onsen owners. Onsen is a hot spot, hot spring in Japanese. So in Japan, we have more than 3,000 hot springs in Japan. And Japanese people want to visit. We have many of onsen owners, they don't like the geothermal energy. So disagreement of the onsen owners. But actually, it's not scientific reasons. It's not scientific reasons. So the onsen owner said, don't touch my backyard. So no scientific reason, but they don't like to touch the onsen, hot springs. So don't touch my backyard. So that is one of the reasons of the geothermal issues in Japan. And another one is the cost problem. The cost problem is a feed-in tariff. So now the Japanese electric company, they have to buy the feed-in system to protect the cost problems, to solve the cost problems. So national park and hot springs cost is a problem in Japan as a geothermal issues. And another one is uncertainty of development, because geothermal energy is on subsurface. It's very difficult to certainty of development and induce seismicity. So in Japan, so we are very, very afraid of this earthquake. So induced seismicity is a very big problem in Japan. So we have to say something about result of the induced site problem. National park, the hot spring, and the cost. That is the political and the economical problems, and we have the several solutions to solve this political and the economical problem. But in this time, so the time is limited. So at the next time, I want to explain how to solve the political and economical problem of geothermal issues. But today, so engineering and technological issues, uncertainty on development and induced seismicity. So in this talk, I would like to explain to overcome the uncertainty of the development and induced seismicity. So advanced technology of geothermal energy is the hot dry rock and the supercritical geothermal energy and the magma energy geothermal. That is the advanced technology. And the power generation technologies, the binary system, the cogeneration system, the electricity and the heat, and the direct use, the heat source. So hot springs, the GHP, the geoheat pump, and the georeactors, the hydrogen production. So this is advance of the geothermal energy. And especially the supercritical geothermal energy, and to produce the hydrogen using the hot springs and geothermal fluid. Anyway, so the mass and energy transport in island the subduction. Some of the audience geologists maybe, but so the subduction is very unique and characteristic circum-Pacific regions. And Japan and Indonesia, we are living in the island arc, and also island arc developed by the subduction system. So in Japan, the Pacific Ocean plate subduct into the Eurasian plate. So in Indonesia, Indonesia's geology is very, very complicated, and also your country is very big, but generally in the Australian plate subduct into the Pacific Ocean plate, and the setting of the Indonesia and Japan is almost, generally almost same. We are living in this island subduction system. So, but the different way. They also like to take baths in onsen hot springs. In monkey in Indonesia, they have no custom to take a bath in hot springs. So the monkey is different. But the geology, the generally and Indonesia. So the conventional geothermal system is the average temperature is 250 and the average depth is 1,500 meters. This is the conventional geothermal system. And the hydrothermal convection like this one. And the maximum seismicity, it's very, because it's a shallow depths, and the brittle conditions. So there is some induced seismicity. But the future technology is the supercritical geothermal energies. The future supercritical, it's the water, the critical temperature is 374 degrees Celsius and 22 megapascal. This is a critical point of pure water above the critical supercritical conditions. So the 400 degree in sea, which is under the supercritical conditions, and the depth is 3 kilometers and 4 kilometers, relatively deep compared to reservoirs. And this is the heat conduction area, and entropy is energy. Energy is 3 to 4 times higher, greater than the conventional system. And if we can get the 450 degree Celsius, at that time, entropy is higher than the university research team are studying about supercritical geothermal energies. Our target is 450, and the depth is 3 kilometers or 4 kilometers. And the target energy is 3 and 4 times higher than the conventional systems. And in these conditions, the low risk for induced seismicity due to the beyond brittle conditions. It's a kind of ductile plastic condition. So this is a cartoon of a supercritical resources. This is a subduction of the plate, and this is a uplifting of magma, and this is a magma chamber. And this, on the top of the magma chamber, there is a porphyritic rocks, and here is a candidate of supercritical fluid. And on the surface, this is a volcano, and also this is caldera. But here is 3 kilometers and 4 kilometers and 5 kilometers. Here is at the top of magma chamber, and also the candidate of a supercritical geothermal fluid. So this is a cartoon of the supercritical geothermal reservoir. So this is a conventional geothermal reservoir. The temperature is 250 degrees in sea, and the average depth is 1,500 meter, 1.5 kilometer. Temperature is 250 to 50 degrees. But our target is here. It's a frontier of the geothermal energy. So temperature is higher than the 400 degrees. And here is heat conductive zones. And the condition of fluid is supercritical. So the scientific and engineering target is, can we estimate and monitor the fluid flow? And how about waterlogged chemical reactions, waterlogged interactions? And how can we create fracture even in a ductile zone? And can we drill into this area? So last 10 years, our research team are studying about can we estimate and monitor the fluid flow in supercritical condition? How about chemical waterlogged interaction? And how can we create fracture even in a ductile zone? And can we drill into the high temperature and high pressure zones? And mostly now we have the national project of the supercritical geothermal reservoirs. 4 years, 5 years. Next year, next physical year, we have to decide which one is the most promising candidate of geothermal. Where is the most promising candidate of supercritical geothermal? We will start the high temperature and the great depth drilling in certain place. So this is enhanced of the engineering geothermal system. And also we can understand the deep structure of volcano and also the mechanism of the earthquake. So in terms of science, the earth science, so it's a very good scientific target to understand the deep structure of volcano and the mechanism of to understand the mechanism of the earthquakes. So in both meaning of the engineering and the pure science, the supercritical here, the critical point. In case of pure water, 374 degrees C and 22 megapascal. This is steam, this is water, and this is ice, and this is fourth state of H2O. That is supercritical. So if we develop the supercritical geothermal reservoir, so we have the Japanese characters, 3 points. Please consider what is the 3 points, 3 important points for development of geothermal energy. 3 aspects, 3 points. So that is heat. Can you imagine? This is fluid. This is fluid. Fluid. Water. Fluid. This is what is this? In Japanese pronunciation is kiretsu. What is this? This is fracture. Okay, we need heat fluid because fluid is a carrier of heat. And we need fracture because fluid can move through the fracture. So the heat, the fluid, 3 important points for development of geothermal energies. The first is heat. So this is Japanese island. This here is Sendai, and here is a volcanic front. Volcanic front means there is a many active volcano along these lines, And this is 1, 2, 3, 1, 2, 3. This is the cross section. This is cross section. This is Japanese island here. There is 50 kilometer, 100 kilometer, 150 kilometer, 200 kilometer. And here is a subducting Pacific plate. And here, red and yellow and green zone, this is the melt, the magma. So we are living here. So, and beneath our house, so one is the magma is upwelling. Cross section number 2, also the magma is upwelling. Cross section number 3, also the magma is upwelling. So Japanese island, we have heat beneath our islands. So the magma is upwelling as related with the subduction upflow related to subduction Pacific plate. And this is the zoom up. This is a Pacific plate subducting into Japanese island. And this is a counterflow. So this is the high temperature magma is upwelling. And here is a volcano, the northeast Japan heat. And so ascending flow of mantle melt. this point, this point, this point, this point, this point. So, and also the 1, 2, 3, 4, 5, the 5 ascending floor. So we said this is a hot. So the subduction and mantle upwelling, and we are living on this island. So we have heat. So how about fluid? So this is the subduction of the Pacific plate, and we can estimate the water pressure. And this is the water supply to the northeast part of Japan. H2O is 13 ton per year per meter. So this is a water circulation, water budget of Japanese island. We can circulation. And our research team published a paper, evaluation in subduction system. The first author is Faja Amanda. Maybe she's now attending the web seminar. She got a PhD. She got a PhD in our lab at the University, and stay until the end of February. Just 1 month later, paper in Geofluid, and she estimated the water supply at 2.3 to 7.6 ton per year per meter. So this is the water supply in Japanese island. Actually, H2O is dominant. And we can estimate the water circulation, water budget in the island system. So we have fluid. How about the fracture? Fracture of the pathway of fluid. So the pathway of heat. So in the classical definition of rocks, so this glass, it's broken by glass. So that is the brittle condition. The ductile is the plastic. This is a deformation, not fade, not fade. So that is just deformation. That is the ductile. So in this definition published in the Core State and the Kirby, in the 1980, about 40 years ago, that is the classical. We published the paper 2017 in the Nature Geoscience. So we have the different ideas. This is the elastic region. This is the plastic region. And for example, the 400 in C, so it's the supercritical geothermal reservoir, even in supercritical conditions above 400 degrees in Celsius. So this is the different the concept of the rock mechanics of the Earth, in the Earth's crust. So, and also we published what is the characteristics of geothermal fluid in the rock. So, but I have to skip this. So it's difficult. It's a little bit high level content. So if you have interest in supercritical conditions, please refer my paper or our research papers. This is time. It's a logarithmic scale and the duration. And this is the depth. So this epithermal gold deposit and the conventional geothermal reservoir and the lifetime of conventional geothermal reservoir. And the porphyry copper system, it's the copper and the gold mining. It's the lifetime is the mining. Lifetime is mineralization is 1 million years, and the depth is deeper than greater than 5 kilometers. And volcanism is at surface, and the duration is 1 year. Sometimes it's 10 kilo years, 10,000 years. And the depth is not so deep, it's shallow. On usually the volcanism is occurred on the surface. And the supercritical geothermal is here. And the lifetime is 10 kilo years and 100 kilo years. The depth is 2, 3, 4, 5 kilometers. That is supercritical geothermal reservoirs. So that is the future technology. So that is the energies as electricity, but geothermal is the thermal energies. So energy is not only electricity, but also heat and other utilities. So geothermal is not only electricity, but also heat and thermal energy. And the direct use is very, very important. And the resort and spa, Japanese students likes the resort, the hot springs like this one, and the industry and greenhouses for agriculture and the small melting, but no meaning. But in Japan, small melting is very important. So this is the direct use, the thermal use. So the GHP, the geoheat pump, is very useful, and also the future technologies. Geothermal is not only for electricity. So this is just 100 and 200 meters, and the subsurface, the temperature is almost same for the during the 1 year. For example, in Sendai, in the summer, it's 30 degrees, but the subsurface only the 15 degrees. And in this winter season in Sendai, the temperature is almost zero, plus minus zero, but the subsurface is constant, 15 degrees. So in the summer season, we can get the 15 degree temperature to the surface, 15 degree air from subsurface. In that case, so it is the resources for heating. So in summer season, the 30, 15, and the winter season 0 to 15, and 23 is a comfortable temperature. We put some energy to heat up the air. So it's good to this summer. So usually, and also in United States and China and Sweden and Germany and France, they already installed the GHP, geoheat pump. Usually, this is a cool country, the United States and China and Sweden and Norway. So the relatively cool and cool to install the GHP as a heat source. But it is popular to install this system into the hot country. For example, Malaysia, for example, Thailand, for example, the Philippines, maybe Indonesia. It is possible to install the GHP, geoheat pump, and for the air conditioner as a cooling system. So in the world, the geoheat pump is for heating, but it is possible to apply this system to cooling. So the Indonesia is a candidate for install the geo heat pump as a cooling system. So electric generation, we need 250 degree, and supercritical SPA is 9 to 100 degrees C, and heat source for agriculture, the 40 and 60 degree, and heat pump only 10 to 15, next future direct use in Japan and also in Indonesia. So another direct use is hydrogen. So this is advanced future technology. So the hot springs consumption, the hydrogen generation. So we are now conducting this future technologies, the production of the hydrogen using the hot springs. The chemical reaction is not so complicated. It's very simple. This is waste aluminum, hydroxide of aluminum, or the oxide of aluminum, and also we can get hydrogen. And the previous common sense, so this reaction needs to the above 250 the high temperature conditions with normal neutral pH conditions. But we test the pH and temperature dependence of these reactions. In 100 degrees C using HCl, so pH 1 is within the 5 minutes. So we can get the hydrogen. This is ideal production to get hydrogen. If the temperature 100 degrees C and the pH 1.5 is like this one, the pH 2 is here. So if we very, very strong acidic pH conditions, it is possible to produce hydrogen using 100 degrees, 100 degrees C here. So it is possible to get the hydrogens under the 60 degree or the 80 degree if we have the pH 1 acidic solutions. So where is the pH 1 fluid in Japan, in the world? So I already mentioned the hot spring in Japan. So mostly the neutral pH, but some of the hot springs is pH 1, 224 hot springs, and the pure pH 2 is 318 candidates. So this is a very good candidate for production of the hydrogen. So we have to go to the acidic hot springs. So the Tamagawa hot springs from Sendai. So this is 9,000 liters per minute, and the pH 1.2. It's terrible. 1.2, and here it's this is natural hot springs in Tamagawa. It's possible to produce hydrogen. So the Tamagawa is here. Tamagawa is here. Sendai is here. Tokyo is Sendai is here. Tokyo is here. Tamagawa is here. It's for almost 400 kilometers. So this is the hot spring area here. After produce the hydrogen, this is Barisan. Barisan is She's now sitting in front of me. She got a PhD. This is the first on-site experiment carried in 2016, and last year we had another on-site experiment in Tamanga Hot Springs, and then she got PhD. So this is on-site experiment among our hot springs. And here is the time and hydrogen production. And so pH is 1.2, extremely low, 100 degrees C. In that case, so using the waste aluminum, we can get the hydrogen using the hot springs. But in Indonesia, here, the east edge of the Java Island, there is a very fantastic volcano. This is the Ijen volcano, the blue fire volcano. It's a volcano, and the blue fire. It's very famous and very fantastic and mysterious sightseeing place in East Java. So I've been to East Java with Amanda and the Barney. So this is the pH 0.3. It's the terrible pH 0.3, but the thing is not. So it's H2SO4 gas and also H2S gas. It's poisoned gas. It's very terrible place, but attractive place. So we developed the simulator to estimate the hydrogen production, and the Zao, and here the Tamanga. I said Tamanga is pH and very good hot springs for production of hydrogen, but EJ is great. EJ is great. pH is 0. In this case, in this time, 0.19, it's extremely low, and the temperature is not so high, but using our in EJ crater lake. Anyway, the hydrogen society, the production of hydrogen, the storage, this is the battery or the storage system, and the fuel cell, and the hydrogen vehicles, and the generation. That is the hydrogen society. So the hydrogen society, the future society, but in the study of the future society, hydrogen. So the hydrogen and the geothermal, usually there is no relation, but in our lab, we're studying about the hydrogen is the future technology for hydrogen sustainable development. So almost one hour. So Indonesia, you have a great potential of geothermal energies. You have a great potential. In Japan, we have experience and the future techs. So unfortunately in Japan, geothermal development is not so enhanced, but Indonesia, you have a great potential for geothermal energy. So if you study the technology in Indonesia and to enhance the sustainable energy and enhance the geothermal energy in Indonesia. Okay, so the final message is let's study together. Let's study together in Japan. So this is our team, Februari, and Bani-san is just sitting in front of me, and Astin is a different room, but she is now attending this web seminar. And Gade-san and Nizar-san, they are sitting in front of me, and next seminar in lab. Anyway, so let's study together in Japan. So we love hot spring. So the final slide of this lecture. So finally, YouTube. Terima kasih. And sorry.
It's the type. It's the type. The right one. I think you already opened it.
Oh, okay. So let's start the YouTube video. This is Kyoyu. Oh. This is the Tamara springs, pH 1.2, and we have on-site experiment in this springs to produce hydrogen. So as a research team studying about the hydrogen drone, so in here, hydrogen, production of hydrogen by using hot springs and then using the hot spring hydrogen, so we can operate drone. So that is another the future technology, the local hydrogen and the drone operation. Okay, so I would like to finish my web seminar. So,
thank you very much, Tsuchiya Sensei, for your very interesting presentation. I believe that we all have many questions, and I see in chat box that there are so many questions. But before we go to Q&A session, first we will take a Zoom photo together. Please, if it is all right for you all to open the video camera. But if you feel uncomfortable, it's all right not to use to open the video camera. So it's up to you. All right. I give to my Pusat Studi Jepang friend Cindy. Silakan Cindy.
Oke, kita mulai ya. 1, 2, 3.
Udah Cindy? Atau masih berkali-kali lagi?
Masih berkali-kali lagi, Bu, sebentar.
Please be patient.
Aduh. Wait. 1, 2, 3. Oke, finish Bu.
Thank you, Cindy.
Yeah.
All right, we will go to Q&A session. But before that, please kindly fill the form, the present daftar presensi, so we can send e-certificate and today's lecture material to your email. The link is on the chat box. Maybe Ibu Susi Aisyah can send the link again so the participants can fill the form. Thank you very much. All right, we will proceed to Q&A session. The first question is from Nur Amin from Turkey. And the question is, what does it mean, the meaning of FIT, feed-in tariff? How much the electrical price resulted from geothermal power? So that's the question.
Okay, so feed-in tariff. Feed-in tariff means the electric company has to buy the renewable energy. And in case of solar energy, in case of geothermal energy in Japan, 27 yen, Japanese yen, so almost $2.5 US. 2.5 US dollar per kilowatt hour. 2.5 US dollar per kilowatt hour. So that is the cost. So the electric company, ちょっとあれを消さなかった。消した?
Bapak Ibu sambil menunggu Tsuchiya Sensei untuk sesi tanya jawab, segini aja dulu ya karena sudah banyak pertanyaan. Ya, dozo Sensei. Hai.
So please shut down the sound. Yeah, the cost of geothermal energy is 2.5 US dollar per kilowatt. No, it's okay. It's okay. It's answer. Otherwise, the solar energy, I can't remember exactly, maybe almost $2. And the wind is $3 per kilowatt hour in Japan. So electric company has to buy the renewable energy. That is a feed-in tariff. It's policy to enhance the renewable energy.
All right, Nur Amin, Mr. Nur Amin, is it answer your question or you want to follow up with another question? Is it okay?
Okay.
Oh, all right, and we have another question again from Mr. Nur Amin. The trend of geothermal in Europe try to develop a low temperature geothermal or binary system due to low in CAPEX and OPEX, shallow in depth well, and etc. What are advantages of supercritical geothermal compared to low temperature geothermal? What are the best technology to be applied in Indonesia based on the current Indonesian geothermal resources on geography? That's the question.
Yeah, it's a very difficult question. Yeah, so low temperature geothermal is very important in Indonesia because you have many geothermal area, and so yeah, but the low temperature efficiency is not so high. It's a problem. Efficiency is not so high. And supercritical is a huge energy, and efficiency is very high. But we have to need the big money to develop. But the low temperature geothermal is low efficiency, but we don't need not so big money for development. So several options. So I have no simple answers. So depends on economical conditions, that depends on local. But at the moment, maybe the low temperature geothermal is it's a very difficult question. Depends on the situation.
All right. Thank you for the answer, TSUCHIYA Sensei. Mr. Nuramin, I hope this answer your question. And we will proceed to next question. It is from Satir Hasibuan-san from Tripatra. So the question is, how about the high concentration of H2S? What is the future technology to handle it? That's the question.
H2S. Yeah, it's very important and interesting question. So H2S is a very big problem for development of geothermal energy, actually. Yes, but it's normal technology is filtering. We installed filter to remove H2S. That is one of the very simple solutions to remove H2S. But so we are studying about the hydrogen production from H2S. So H2S, if we remove sulfur, so after that we can get hydrogen, H2. So one of the future target is to produce hydrogen from H2S. So to take a geothermal fluid and with H2S, so geothermal fluid to generate electricity and H2S to produce hydrogen. So that is the binary system. So different meaning of binary system to produce electricity, to produce hydrogen from H2S. So, but that is the future technologies.
Okay, thank you very much, TSUCHIYA Sensei. Pak Satir, is it answer your question or you want to follow up again?
Okay. Number 4.
Okay, clear. Okay, the next question. This is from my colleague, Ibu Lea Santiar from Center for Japanese Studies. It is not on the chat, but she asked by WhatsApp to myself. And the question is, are there any risk if we develop geothermal for daily usage?
They use daily usage?
Yes.
What's the meaning of daily use the disk? Geoheat pump? You mean geoheat pump daily use?
Yes.
Sehari-hari.
Are there any risk if we develop geothermal for like we use it at our home for daily use? Is it possible?
for our electricity or our electricity.
Oh, I think it's not so big risk. We have not so big risk.
For example, like we use nuclear for our electricity, so they say there are risks about the nuclear sources. But if we use thermal, it's okay.
Oh, unfortunately, I can't hear. Not so clear. So please say once more again.
If we develop the geothermal resources, is it okay for the what do you say, the mountains or the magma? I don't really know the
They have read there is a
Okay, so if we develop the geothermal energy, so the organic eruptions or the big earthquake, so we estimate such kind of big the natural disasters.
correct.
Okay, that is the question.
Yes, thank you.
Okay. Yeah, really, actually, so maybe it's don't worry about such eruptions. But we can design the geothermal reservoir, so it is maybe there is no risk for organic eruption, but we have some induced seismicity. We have some risk of earthquake. But magnitude is not so high, maybe magnitude 3, and the highest is magnitude 4. And usually magnitude 1 or 0, and some mostly magnitude -1. So it's very small. In English word, it's the microseismic, or sometimes we say acoustic emission, AE. It's very small. It's not earthquake, just vibration. So I think actually we have some induced seismicity, but it's not so high risk, I guess. And usually the induced seismicity is very low. We cannot feel such seismic. So I think compared with the nuclear energy, geothermal is very, very safety energy resources.
All right, thank you very much for the answer. And we will proceed to the next question. This is from Bapak Abdul Halim. The question is, as you know, the range temperature steam in Indonesia from well is about 190 to 200 degrees Celsius. In case to reach supercritical, should we drill more deeper? And what's the risk that can be happen? Thank you.
So nobody knows. so you can get the 200 hot water. So is it possible to estimate 400 degree? Nobody knows. So it's very difficult to answer. so we need some exploration. We need geological survey. We need geophysical survey. We need geochemical survey. So geothermal is not so simple. So not only temperature, we have to think all conditions of the geology. So it's not so easy to answer. If we can get the 200 degree solutions, we have 200 fluid. It is possible to get 400. It's nobody knows. We have to study.
All right. Is it clear, Bapak Abdul Halim, or you want to follow up with another question or discussion? Yeah. Oh, okay. I will proceed to the next question. This is from Bapak Naufal Nardalia Arsyad from Bandung Kokadaigaku or ITB. Which one is more feasible? Develop many medium to low temperature geothermal using binary plant, or deep or high temperature system using conventional flash system?
Yeah, it's also a difficult question, but it's both. So in local society, maybe the low temperature binary system is very, very efficient. So I'm not sure the electric condition in Indonesia, but still now some people cannot use electricity for 24 hours in a day. In that case, low temperature generation system, the binary system, is very useful for supplying electricity to local people. But if you want to develop some industry, which means industry needs a huge electricity. In that case, a conventional style geothermal energy is useful for growing up the industry. But for the ordinary life in local area, so low temperature and the binary system is useful for supply electricity to local people. So the different targets, different purposes.
Okay, thank you, Tsuchiya Sensei. Pak Naufal, bagaimana? Apa mau melanjutkan dengan pertanyaan lanjutan? Do you want to follow up to another discussion to Mr. Naufal? Is it make sense? Okay, thank you. Okay. All right. Before we proceed to another question, I say it again that please kindly fill the form so we can send e-certificate and today's lecture material to your email. So maybe Center for Japanese Staff can once again put the link in chat box so our participants can click the link and send and fill the form. Thank you very much. So we will proceed to another question. This is from Mr. Surya Silitonga from PGE. The question is, as Indonesia and Japan that are located in Ring of Fire, any plan about geothermal power plant in the future to facing natural disaster, such as earthquake, to minimize mitigation damages in properties, and to saving people or operator, as has happened in Japan? There is any emergency plan that used in Japan's power plant as a best practice? Thank you.
No, it's a question. It's just opinion. Just
Surya, Mr. Bapak Surya Silitonga, apakah ini pertanyaan atau mungkin ini sebuah komentar?
Yes, it's a question, sir. Tsuchiya-san. Friendly asking about best practice in Japan, geothermal power plant. When natural disaster happen in Japan, what the emergency plan that exists in Japan so we can adopt it in Indonesia? Because currently in Indonesia, we didn't have any emergency plan in the power plant when natural disaster happened. Thank you.
What emergency plan?
Is there any emergency plan that used in Japan's power plant that we can apply also in Indonesia?
Something.
Is it right, Surya, Bapak Surya?
Yes, Ibu Ruli.
Mungkin bisa satu kali diulang kali ya pertanyaannya kepada Pak Tsuchiya gitu.
Okay. Tsuchiya Sensei, friendly because Indonesia are located in Ring of Fire and many geothermal power plants built in the mountain. So like happened in Japan, there is any emergency plan that existing in Japan's power plant to facing natural disaster, to saving equipment or to saving people.
Oh.
Thank you, Tsuchiya-san, Sensei.
Oh, I can understand the meaning of questions. Yeah, maybe in Japan we have different feeling. For example, 10 years ago, 2011, we had a very big earthquake. It's a very big natural disaster. And at that time, nuclear power plant in Fukushima was destroyed. But geothermal power plant in Japan, so it's very, very safety. All of geothermal power plant are operating during earthquake and after earthquake. So in Japan, geothermal power plant is very, very safety compared with other power plant system. For example, nuclear, for example, thermal power plant. So nuclear is very safety system. So, and also in Japan, we can monitor the volcanic eruptions. So maybe in Japan, the geothermal, many people believe geothermal is very safety power plant compared with other power plant.
Is it answer your question, Pak Surya? Or you want to follow up again?
I think it's enough. Thank you very much, Tsuchiya Sensei.
All right, thank you, Papa Surya, for the question. So we proceed to the next question. This is from Fitri, my student at Japanese Studies Department, Universitas Indonesia, and she sent the chat privately to me. So this is the question. Tsuchiya Sensei, based on the presentation, the slurry of the steam process is injected to the ground. Why not be extracted? And is there any value left in the slurry? So that's the question. The question.
Okay, good question. So geothermal fluid, it's a sustainable system. So if we can take hot water from the underground and they waste the hot water, that is sustainable. That is not sustainable system. So, and also geothermal fluid is not so clean. So geothermal fluid can contain some amount of toxic elements, for example, arsenic, for example, sulfur. So we inject the geothermal fluid into the subsurface again. So because we don't take care of the toxic fluid. So please back to the nature. So that the circulation system is better for good operation and safety and environmentally friendly operation. But if the fluid, geothermal fluid can contain some amount of the good element, for example, gold, for example, the copper, for example, the zinc. In that case, we can extract gold or other metal elements from fluid. And the rest of fluid, we inject fluid into the subsurface. So we can take some the noble and good element if possible. So that is a geothermal system, sustainable system.
All right, thank you, Tsuchiya Sensei. Fitri-san, is it clear enough or you want to follow up?
Clear, Sensei. Arigatou gozaimashita.
Hi, arigatou gozaimasu. All right, we will proceed to another question. This is from Dina Ardianti. Thank you so much for the lecture, Tsuchiya Sensei. Very informative and useful. And my question is, how do you think about Mount Merapi in Sleman? Could it be the one of geothermal energy in Indonesia in the future? If yes, do you have suggestion to Indonesia to manage this potential geothermal energy?
Okay. So due to COVID-19, if there is no virus, I want to visit and I want to do the field survey, but at the moment I have no information.
All right, Dina, Ibu Dina, is it clear enough? Okay, we will proceed to another question. There is Maura Firdausya, and she told me that she wants to ask question by herself. So I give this chance to Ibu Maura to give her question. Ibu Maura mungkin bisa diaktifkan video kameranya dan di unmute silakan.
Oh, mohon maaf untuk kamera videonya karena sinyalnya agak buruk mungkin jadi agak.
Oh, oke, ya, tidak apa-apa, silakan.
Baik. Oke. Tsuchiya Sensei, thank you so much for the insightful lecture. ジャカルタナショナル大学のものです。マウラと申します。科学とテクノロジーは、私の専門ではありませんので、プレゼンテーションを聞いて、ちょっといくつかお聞きしたいことがあります。先生がおっしゃった通り、確かに地熱エネルギーは大きいポテンシャルがあります。ですが、その地熱エネルギーに何か副作用はありますか？例えば、地熱を開発するため、逆に将来副作用が起こる可能性もありますか？そして、もし太陽エネルギーと比べると、どちらが安全でしょうか？
Alright, okay. Thank you Maura-san. Maybe I will, mungkin saya terjemahkan sedikit aja dalam bahasa Indonesia untuk pertanyaannya karena mungkin Bapak Ibu di sini tidak semuanya berbahasa Jepang. Jadi intinya Ibu Maura menanyakan apakah ada efek samping begitu ya dari geothermal energi. Apakah betul Bu Maura? Saya agak takut juga nih kalau salah.
Betul sekali.
Betul ya. Ya kurang lebih seperti itu. Nah, 土屋先生、質問皆様が分かるように英語でお願いいたします。
So thank you very much for your question. First question is how about the effect of development of geothermal energy? Can you hear me clearly?
Yes, I do. I can hear you clearly.
It's okay?
Yes. Yes.
So first question is how about the effect of development of geothermal energy? So there is some side effect. One is the induced seismicity. So the development of geothermal energy enhance the earthquake. I mean the artificial earthquake. We say induced seismicity. But the induced seismicity, induced earthquake is not so big. The magnitude is -1, 0, 1, or 2. The maximum is magnitude 3 or 4. It's not so big. And if magnitude -1, 0, or magnitude 1, and it is impossible to feel by human. So actually, there is some side effect, but it's not so effective for human ordinary life. That is one of the side effects. And the second question is, how about the safety or security of geothermal energy compared with solar energy? Yeah, so it's very difficult questions, but the solar energy is not so risky energy because only we have to put on the solar panel on the ground, the solar panel on the roof. So it's not so risky for the ordinary life. But in Japan, maybe in Indonesia, there is some problem because we need a huge area for solar panel. So in Japan, the view or scenery is not so good. And some of the forest is occupied by solar panel. It's not so good scenery. It's not so good view. For example, from the viewpoint from the mountain, we can see the many solar panels. It's not so good. But the geothermal is a point. It's not so huge area. So solar is not so high risk, but there is some environmental problems. So maybe near future, the solar has such kind of environmental problems. And also the solar energy, I already mentioned during the lecture, the efficiency is very low, only 12%. So if installed capacity of solar energy, 10 megawatt solar energy is very huge area, 10 megawatt installed capacity. But actually, efficiency is only 12%. In that case, which means 10 megawatt installed capacity means only 1 megawatt production. So that is the problem of solar energy. But in geothermal, 10 megawatt installed capacity can produce 10 megawatt electricity. So it's a different concept. So the different environmental effect. So please consider which is the risky, which is safety. It depends on the land, depends on the scenery, that depends on the economic conditions, and that depends on the local government. So we have to think about everything. But we have several options. So in this case, solar is better. In this case, geothermal is better. In this case, wind is better. So we have options. That is very important.
All right. Is it clear, Maura-san?
いや、mungkin もう一つお願いします。先生、よろしいですか?
Okay.
So if the geothermal energy increase the potential of getting earthquake, because different with Japan, in Indonesia, our buildings are still kind of not as strong as Japanese buildings. So maybe it will take some time for Indonesia to be ready to develop the geothermal energy. So do you think how much time do we need to prepare the country to be ready to develop this geothermal energy to become to be ready to use for the electricity or the other use?
It's very difficult to answer for me. Yeah, it's difficult. So that depends on the society. So I can't answer.
All right.
Sorry.
All right. Thank you, Maura-san, for your questions. And we still have two questions from Alivierino Yusuf Kresnawan and Krishna Pratamalaya, and one comment for Nur Aming. I will read the comment after Sensei answers these two questions. So the first one is from Alivierino. Can geothermal energy be applied to another planet? For example, for example, to Mars planet. That's the question.
Yes. Good questions. Oh, very interesting. Yeah, maybe. Yeah, so us, we have plate tectonics, but in Mars, the plate tectonics, it's not so clear, but the plate tectonics is already finished in Mars. So the Mars is, how to say, the core, the planet. But in us, we have a core and the mantle convections, and we have a magma. But and also we have a plate tectonics. But in Mars, so maybe the plate tectonics is already finished. So it's very difficult. But in the no Jupiter, so Venus, it's possible maybe, but Venus is very hot planet and the CO2 dominant. So it's very hot planet, so it's no meaning for develop geothermal. It's very interesting. It's a dream, but difficult to answer. Okay, but it's a dream.
All right. So we proceed to the last question from Krishna Pratamalaya. The question is, thank you for the lecture, Tsuchiya Sensei. In broad sense, in Japan, is there plan to replace fossil-based power generation with geothermal-based power? And what is the constraint for this?
Yeah. So, but actually, the fossil energy, almost 90% of energy is supplied by fossil. So, yeah. Yeah, maybe the government target until 2050. We have to create a carbon-free, carbon-neutral society. So 2050, we have 30 years. So during the 30 years, we have to replace the fossil power plant to another power plant. But another technology is fossil energy. We produce the CO2, but we have to think, we have to study about the CCS, carbon capture and storage, or the CCUS, carbon capture, storage and utility. Of that, those kind of structure is the next technology to reduce the CO2 emissions. So if we can develop such kind of technology, CCS or CCUS, in that case, the fossil energy can survive. So in Japan, so maybe the fossil energy is getting down, and but it's I think it's not so. It's difficult to reduce to zero. We keep some power plant of the fossil power plant, but instead of fossil power plant, we have to develop the CO2 treatment technologies, CCS, CCUS. That is the current answer.
All right. Thank you very much for the answer, Tsuchiya Sensei. So to close this question and answer session. Oh no, all right. This is Yoga Amran. Maybe he responds to the one that asked about is it geothermal energy can be used in Mars, right? So we can read together. So to close this question and answer session, I would like to read Nur Amin, Bapak Nur Amin comments. Thank you, TSUCHIYA-san. I agreed that not a simple answer. The supercritical geothermal technology like crossing the mainstream current geothermal technology. Geothermal player try to get as much as lowest in CAPEX or capital expense and OPEX or operation expenses. Supercritical geothermal like out of the box technology with lot of questions from geothermal players. Since lot of issue to be resolved in terms of high temperature, high pressure, high enthalpy, and high chemicals content issues. So this is still need a long study. So this is the comment from Nur Amin-san.
That's right, but we have some in Iceland and Italy and the United States, Russia and Japan, and New Zealand. We have the supercritical projects in several countries. So it's yeah, of course we need time, but it's a future target.
All right. Thank you very much, TSUCHIYA Sensei. So we come to the end of our lecture today. Maybe for closing this lecture, maybe TSUCHIYA Sensei, do you have like one final statement to make us more aware for using this geothermal energy and how we can develop this together, Japan and Indonesia, please.
Okay, so thank you very much for giving me the opportunity to give a lecture through web. And it's a great honor to have the lecture for the audience in Indonesia through web. And I have been to Indonesia many times, more than 20 times. And also we have the Indonesian student. They are very great students. So, and unfortunately, the last year, 2020, I couldn't visit the Indonesia due to the COVID-19. But after the coronavirus issues, I really want to visit Indonesia once more again. And also, for example, the Bandung and for example, Malad, it's a very beautiful city. Unfortunately, Jakarta is a little bit clouded, so, another city is very beautiful and the natural taste is very comfortable for me. So the near future, I would like to visit Indonesia once more again. And also, please try to come to Japan to study the geothermal and the environmental issues. So our department, our graduate school is a graduate school of environmental studies. We can cover many fields of environmental issues, the energies and the resources, the waste problem, the water problem, and the human and nature relations, and so on. So please, interested in the TOHOKU University and our schools. And please interest in Japan. So we have snow. My hobby is skiing. So thank you very much. Thank you very much for attending these lectures. So I want to study with the young generation students. Thank you very much. Terima kasih.
Thank you very much, TSUCHIYA Sensei. So for anyone interested in geothermal energy, maybe we can start by checking the web of Graduate School of Environmental Studies at TOHOKU University and follow up furthermore. So maybe we can give our reaction to appreciate this lecture today by maybe clap hand or give some reaction in your Zoom feature. Unfortunately, we come to the end of our lecture today. Thank you very much for all the participants, and for, of course, for Embassy of Japan in Jakarta, Takahashi-san and all the staff for co-organizing this system, this lecture. And of course, thank you to TSUCHIYA Noriyoshi sensei and all the Indonesian students there for contributing for this lecture. Hope we can meet again in another ambassadorial lecture, and stay healthy and stay safe. Thank you very much.
Thank you.
Domo, otsukare sama deshita.
Otsukare sama deshita.
Takahashi-san, domo, otsukare sama deshita.
Otsukare sama deshita.
Terima kasih banyak.
Terima kasih banyak.
Terima kasih banyak semuanya.
Ya, terima kasih banyak Bapak Ibu semuanya.
Terima kasih.
Terima kasih.
Terima kasih.
Terima kasih.
Amanda.
Bapak Ibu peserta, mohon maaf habis ini kami ada sedikit internal meeting lagi, jadi Bapak Ibu silakan tidak perlu sungkan jika perlu meninggalkan Zoom dulu. Terima kasih banyak atas kehadiran Bapak Ibu sekalian, dan semoga kita bisa bertemu lagi di lecture-lecture Ambassador lecture berikutnya. Terima kasih banyak Bapak Ibu.
You had 199 participants.
Ini